Hi, I'm Professor Afshar at Glendale Community College. This is Physics 101, Lecture 10. In this lecture, we'll discuss two-dimensional motion. This topic is covered in Chapter 4 of our textbook by Surway and Jewett. So far in the course, we've been discussing one-dimensional motion. That motion might be horizontal along an x-axis, or it might be vertical along the y-axis. But the motion that we've been discussing has always been along one dimension at a time. Going forward, we want to talk about two-dimensional and eventually three-dimensional motion. We'd like to talk about the motion of objects that are simultaneously moving in the x direction and in the y direction. To help us understand that kind of a motion, consider the scenario depicted here. We have a car. Initially, it is located over here, and a few seconds later, it is located over here. Based on our coordinate system, we can see that the initial position of the car is represented by this green vector here. To be a little more precise, we can say that at some initial time, let's say 0, the car has position 2, 5. Notice we're using vectors to represent the two-dimensional motion of this automobile on a two-dimensional grid. Let's say 5 seconds later, at some final time, the same car is now located further away, as indicated by this blue arrow. You can count the squares on this grid and you'll see that the final location of the car, represented by R final, is 9, 7. Notice that in this two-dimensional world, we're using the letter R to denote position, not X, not Y, but R, and we're putting arrows above the position vectors. What is important often in the motion of an object is the displacement of the object. The displacement of the object is defined as the change in its position. We denote displacement by delta R. Remember, R refers to position and delta often denotes change. So displacement is really a change in the position. Final position minus initial position. At this point, we should know how to subtract vectors from one another. Remember that when we're subtracting vectors, we do component-wise subtraction. So RF minus RI is really 9 minus 2, which gives us 7. And then we have to subtract 7 and 5, which gives us 2 over here. So 7, 2 is the displacement vector representing the motion of this object. And here on the graph, I've shown the displacement vector using this orange arrow. You can see that the orange vector points from the initial position to the final position. And if you count the squares, you will see that indeed to get from the tail of this vector to the tip of this vector, we must travel 7 squares, or 7 units along the x direction and 2 units along the y direction. Hence the coordinates 7, 2. Notice that this displacement vector refers to the shortest path between the initial and final positions. So we don't know if the car actually traveled along this path. If this is, for example, the grid of city streets, the car may have traveled due east and then north and then east and then north, may have followed a zigzag pattern. It's not really clear. We don't have that history. The displacement vector simply refers to the shortest path or the most direct path between the initial and the final position. In calculating the displacement vector for the motion of an object, we had to use a coordinate system so that we could write down the initial and final positions of the object. Here I'm displaying another coordinate system that is a little bit displaced relative to the original one. The coordinate system we were looking at on the previous slide had its origin over here. Our new coordinate system has its origin over here. Remember, you're always free to choose your own coordinate system. Parameters in a problem that are significant should be independent of the choice of the coordinate system. How would we calculate the displacement of the same vehicle using our new coordinate system? Well, with the new coordinate system, the initial position of the car, R sub I, is now minus 2, 3. Notice that it's the same initial position and the same final position as before. What has changed is the coordinate system. What has changed is the origin, or the 0, 0 of the coordinate system. In this new coordinate system, in order to get from the tail to the tip of this arrow, we must travel 2 units in the negative x direction and 3 units in the positive y direction, hence -2, 3. 5 seconds later, the final position of the same car is now 5, 5. You can see that because of the change in coordinate system, the initial and the final positions of the vehicle have now changed. At least numerically, the vectors that we assign to those positions have changed. However, the displacement vector has not changed, and this might be a little bit surprising. Delta R is still defined as the final minus the initial. If we actually carry out this calculation by doing component-wise subtraction, for example, taking 5 minus a -2 gives us 7, and then 5 minus 3 gives us 2, we find that the displacement vector is exactly as it was on the previous slide. So the conclusion here is that the displacement vector is independent of the coordinate system, and this is an important property of the displacement vector. In order to be able to talk about the position vector, we need a coordinate system. The position vectors numerically depend on the choice of the coordinate system, but so long as we're talking about the same car with the same motion, the displacement vector will always be the same vector. In particular, a vector that points directly from the initial position to the final position. The fact that the displacement vector is independent of the coordinate system is important to us because it allows us to define other motion variables such as velocity and acceleration. Once again, consider this scenario of a vehicle, a car, driving from some initial position to some final position over a 5-second interval. Its displacement vector, this orange arrow, is 7, 2. The displacement vector allows us to define the average velocity vector of the car. The average velocity vector is defined as the displacement vector divided by the time interval. The displacement vector is 7, 2. Delta t is simply the time interval we're considering from 0 to 5 seconds, so we need to take this vector and divide it by 5. Dividing a quantity by 5 is the same thing as multiplying that quantity by 1/5, so I've written this expression as 1/5 times the vector 7, 2. At this point, you should know how to multiply a scalar by a vector. So we have the number 1/5. To multiply it by the vector 7, 2, we distribute it into the vector. So we multiply the x component and then we multiply the y component. And the resulting vector is 7/5, 2/5. This vector represents the average velocity of the vehicle over this 5-second interval. Notice that the average velocity, represented by the red arrow, points in exactly the same direction as the displacement vector. That's because when you multiply a vector by a scalar, you don't really change its orientation, you just make it longer or shorter, depending on what number you're multiplying by, but the orientation of the vector is preserved. So remember this important fact that the velocity vector and the displacement vector always point in the same direction. You might be wondering why we call this the average velocity and not the velocity or the instantaneous velocity of the object. And the reason is that we don't really know what the car was doing during this 5-second interval. If the car was driving on busy city streets, then it might be slowing down or it might be speeding up at different times. What we know is that on average during this 5-second interval, its velocity was 7/5, 2/5, but at certain times it might be going faster and at other times it might be going slower than this average value. If you want to know the actual velocity of the car at a particular instant or one specific moment in time, then you shouldn't be considering a 5-second interval, you should be considering a 1-second interval. Or better yet, you should be considering a millisecond interval. Or better yet, you should be considering a nanosecond interval. In fact, if you really want to know the velocity of this car at one single instant in time, you should take the limit of the average velocity as delta t goes to 0. Hopefully you remember from your calculus days that that particular limit is really the derivative of the displacement vector with respect to time. We'll come back to this idea in just a few minutes. Before discussing instantaneous velocity and acceleration, we should take a detour to discuss decomposition of motion. As it turns out, two-dimensional motion can be viewed as two separate and distinct motions, one along the x-axis and another along the y-axis. For example, imagine throwing a baseball across the field. That baseball might be moving forward while simultaneously rising in elevation, traveling along some diagonal trajectory. To best understand the motion of the baseball, we need to separately analyze its motion in the x direction and in the y direction. This idea of separating the motion into two distinct motions is referred to as the decomposition of motion. So in this context, decomposition of motion refers to separating motion into two distinct components. This idea was first introduced by Galileo circa 1638. Galileo was interested in the motion of an object rolling off the edge of a table. So imagine you have a ball rolling along on a horizontal table, reaching the edge of the table, and then eventually flying off the edge and hitting the ground. Galileo was interested in knowing how long it takes for the ball to hit the ground, or how far away from the base of the table the object will hit the ground. He was also interested in knowing in the exact shape of the trajectory that is followed by the ball as it flies through the air. He realized that to answer these questions, it was best to separate the motion of the object into x and y components. You could almost imagine that there are two objects in motion. One of them is moving only in the x direction, and the other one is moving only in the y direction. Looking at this picture, you can see that the x motion is uniform motion, meaning that the distance that is covered in each time interval is equal. So every second that elapses results in the object traveling the same exact distance. This tells us that the velocity of the object in the x direction must be constant. By contrast, look at the y motion of the object. As you can see, the intervals that are traveled in each time interval, every second, let's say, grow bigger and bigger and bigger. This tells us that the velocity of the object in the y direction must be increasing, or that the object must be accelerating in the y direction. There's a lot that we need to understand here. To begin that process of understanding this type of motion, we need to talk about x velocity and y velocity separately. Galileo's suggestion for the decomposition of motion implies that all of the motion variables must now be divided into separate components, specifically position, velocity, and acceleration. Each must now consist of two independent quantities when we want to analyze two-dimensional motion. Specifically, when we're discussing the motion of a ball rolling off the table or a baseball flying across the field, we need to discuss its x-coordinate, and then we need to discuss the rate of change in the x-coordinate, which we'll call the x-velocity, and we also need to discuss the rate of change in the x-velocity, which we'll call the x-acceleration. At the same time, we need to discuss the y-coordinate of the object and the rate of change in the y-coordinate, which we'll call the y-velocity, and the rate of change in the y-velocity, which we'll call the y-acceleration. These equations should look familiar to you from Chapter 2. The new idea here is that now we have twice as many quantities to worry about. We're going to talk about the x-coordinate and the y-coordinate at the same time. We're going to talk about how the x-coordinate is changing and how the y-coordinate is changing separately. So that'll give us x velocity and y velocity. And of course, each one of those velocities could be changing, which we denote by x acceleration and y acceleration. To facilitate the writing of all of these quantities, we sometimes combine x and y into a single vector, which we'll denote as vector r. The arrow above r reminds us that r is really a vector quantity. It refers to two distinct numbers, x and y. We'll also talk about the velocity vector. Again, the arrow above the v reminds us that we're talking about two distinct quantities, v sub x and v sub y. V sub x is the rate of change in x, and v sub y is the rate of change in y. We'll often simplify the equations by simply writing v is equal to dr dt, but remember that these arrows are reminding us that there's actually two distinct components that we must worry about. Similarly, we'll talk about the acceleration vector, and you have to remember that the acceleration vector also has two components, one in the x direction, one in the y direction. In some sense, if you want to discuss two-dimensional motion, you basically repeat everything that you did for one-dimensional motion. It's just that now you have two sets of equations referring to two sets of motion variables, one in x, one in y. So here's a practice problem that demonstrates some of the ideas we've been discussing. A race car is a distance delta x from the finish line. It is moving with constant speed v at an angle of 40 degrees with respect to the x-axis. When will it cross the finish line? So here on the right side, we have the finish line of a race, and we have a car that is only 100 meters away from the finish line, but for some reason, let's say the car is out of control, and it's not moving directly towards the finish line. It's moving at an angle of 40 degrees. The speed of the car is 10, and the distance from the finish line is 100. We want to know how many seconds it will take for the car to reach the finish line. In some sense, this is a relatively straightforward problem. We are going to find out the distance that the car has to travel and divide it by the speed, and that'll give us the time. The real question is, what distance should we use? Should we use delta x? After all, this is the distance, the shortest distance from the finish line to where the car is located. Or should we use a different distance, like this distance here? If the velocity of the car is along this diagonal direction, then perhaps this is the distance that we should be using in calculating time. It turns out we can use either distance. Which distance we use depends on our approach to the problem. It depends on whether we want to decompose the motion or not. So one approach to this problem basically goes like this. We can say that if the car is moving along a diagonal, then we're interested in distance d. With a little bit of geometry or trigonometry, we can see that there's a right triangle here. We can say that the cosine of theta, or 40 degrees, is equal to delta x over d. Remember that cosine is adjacent over the hypotenuse, so that's delta x over d. And by rearranging this equation, we can find that d must equal to delta x over cosine of the angle. And now we can take this distance, delta x over cosine of 40, and divide it by the speed of the car, which is given to us as 10 meters per second. And if we put all of that into our calculator, we find that the car will reach the finish line in approximately 13 seconds. In this approach to the problem, we have not really decomposed the motion. The object is moving along a diagonal direction, and we've simply taken that diagonal distance. Another approach to this problem, which would give us exactly the same answer, involves decomposing the motion. Here we can say that if the car is a distance of 100 meters away, this is the distance we're going to use, 100 meters. However, we now have to recognize that the velocity vector has two components. It has a component in the x direction, which we can call v sub x, and it has a component in the y direction, which we can call v sub y. We can figure out the x component using trigonometry. So again, by looking at cosine of 40 degrees, we remember that it must be adjacent over hypotenuse. Cosine of 40 degrees must be Vx over V. Rearranging this formula, we find that Vx must equal to V cosine of the angle. So now we're going to take the distance delta x and divide it not by V, but by V cosine theta. So the idea is to take the distance and divide it by the speed in that direction. Since we're talking about delta x, that's the distance in the x direction, we should not be using V, but the x component of V, which is V cosine theta. Putting all of this into your calculator, you will get exactly the same number, but this second method of calculation is a little more sophisticated and more in line with what we want to do going forward. We want to look at velocity and consider its x and y components separately. Here's another example demonstrating the decomposition of motion. The position of an object is described by this function. Notice I'm giving you the r vector, which is the position vector, as a function of time. Notice that the r vector has an x component and it has a y component. And also notice that the x component depends on time and the y component depends on time as well. So if we wanted to, we can denote this whole thing as x of t, and we can denote this whole thing as y of t. Given this information, calculate the acceleration of the object at t equals 2 seconds. Well, we know that acceleration is the rate of change in velocity. More precisely, acceleration is the derivative of velocity. And we also know that velocity is the derivative of the position. So we're going to start with velocity. Given the position vector, we're going to calculate the derivative of its x component and its y component. And we will find that the x component of velocity is 6t squared. So that was obtained by taking the derivative of 2t cubed plus 6. The y component of velocity is simply the derivative of the y coordinate. You should remember that the derivative of a sine is a cosine. You should also remember that when you take the derivative of a sine function, you also need to take the derivative of its argument, the thing inside the parentheses, and that's how we ended up with pi over 2 out front. If you want, you can now think of this whole thing as v sub x, which depends on time, and you can think of this whole thing as the velocity in the y direction as a function of time. The question asks for acceleration, so we need to do another derivative. We're going to take the derivative of 6t squared. That's going to give us 12t. We're going to take the derivative of the cosine function. Remember that the derivative of a cosine is minus a sine. And we're going to take the derivative of its argument as well, which gives us another pi over 2. Multiplying with the old pi over 2 gives us pi squared over 4. Now we're not done yet because the question asks for the acceleration vector at a specific time. Specifically, we want to know what the acceleration is at 2 seconds. So now we need to plug in 2 for t. When we do that, we find that the acceleration vector at 2 seconds is 24, 0. The 0 comes from the fact that sine of pi is 0. And that's the end of this lecture. Thank you for your attention.